your time changes and you have your space changes. And this was, Maxwell saw this, and he saw this constant here, which he recognized as the velocity of this wave phenomenon. So we plug in the numbers. Now this is the most remarkable thing. Those numbers, epsilon naught and mu, were developed from static charges, right? We said Coulomb's law, and we're going to put in a k, or we're going to call it epsilon 0. So it has to do with static charges, nothing to do with light, nothing to do with motion. Yet that epsilon naught comes in to this parameter, which is, turns out from the wave equation. You don't remember the wave equation, but that was a velocity squared. And what you get is that, and also this constant that came out of Biot Savart that they needed to account for a current producing a magnetic field. They had to put in a mu 0. When you put that in, Maxwell plugged in the numbers, and he got 3 times 10 to the 8th. Well, 40 years before this, someone actually measured the speed of light and came out with 3 times 10 to the 8th meters per second. So that was an aha moment that even a sedate person like Maxwell must have jumped out of his seat when he saw that he was producing a wave of electricity and magnetism which travels at the speed of light. So maybe light is electromagnetic radiation. And then it has this other property of the ratio E over B is C in vacuum. And one of the things that you want to recognize is that it turns out that it doesn't matter what the frequency is, nor the wavelength. All radiations in vacuum travel at the speed of light. Whether it be very fast, very slow, it will travel at the speed of light in a vacuum. Now, the other thing I should, well, let me just go on to the next joke, which is that you know you've made it, they make a t-shirt about you, and this is one where God said Maxwell's equations, and there was light. So it's a little irreverent, but cute, I guess. So the next one is that, let me see, there's something missing here. So all these waves, electromagnetic waves, travel with the speed of light through empty space. So for example, if a star blows up someplace and emits X-rays and gamma rays and light and heat waves and everything, all those waves arrive here at the same time. And we count on that. Yes, sir? Ah, yes, well, that's the next thing, right. You're one step ahead all the time. Now you're only 2 minutes ahead. Yes, today you're already 1 day ahead. Next question will be 2 weeks ahead. But that's a good question. So in a vacuum, yes, and that's interesting because all things have the same speed. So if you have a radar pulse, like the cops are watching you with radar, their radar radiation is going, they think, at the speed of light. And they count on that. But in a material, this is your point, if there's material in between, the light changes its speed, as you might think. And in fact, it typically slows down by a factor of n. Which is what we call the index of refraction, very important parameter. Moreover, when you go through a material, this n, the slowing of the light, depends on the wavelength and the frequency. We'll get into that. The different slowing of light means different colors of light travel with different speed. Because wavelength and frequency are related to color of light, in the case of light, and that will depend on the wavelength and frequency. And we'll explain that. We'll understand. This was a very important thing to try to understand why the velocity of light changes in a material and why it changes with frequency in a material. And it's in fact the reason there's a rainbow. It's because in a material, like in little drops of water, the red light travels with different speed than the blue light, and so it separates in a raindrop, and that's why we see different colors in a rainbow. And a lot of other very important things, like my glasses. The light slows down when it passes through the glass, and it bends because of that. This is known as refraction. Familiar with refraction? You will be, because you're going to be doing it in the lab this week. At the end of this week, you'll certainly be familiar with it. Okay, and well, that's a very interesting phenomenon, this idea of slowing down, because the idea is that if you, we'll see more of this in very great detail, but if, for example, light comes in at an angle into some material where you have a different n not equal to 1, now you're coming from n equals 1, let's say air, and you come into, say, glass. What happens is your light is coming in like something like this. Now, this part of the beam hits the material first, and it slows down. It's sort of like soldiers marching into the mud. These guys go much faster. So by the time they arrive, their brother here has advanced not so far. And so what happens is that the beam of light changes its direction and bends toward the slower medium. Because this part of the beam has been in the medium longer than this, and so it's slowed down, so the whole front changes. We'll see that. You're going to see that in your lab. So the fact that the speed of light changes from air to a medium is, and that's why we have glasses and lenses, all kinds of things like that, come from this refractive effect, the fact that light changes. And in principle, different colors would refract differently, and they'll bend differently. So that's why you can spread the color. That's what Newton did way back when. What he did, he had a prism, and he took sunlight and passed it through, and the different colors refracted differently. So he spread out the red and the blue, and you could see that because different wavelengths have different colors. Things will make sense after a while, I think. So here's another repeating this property that the ratio of E to B is always equal to the velocity c, and the direction of propagation is E cross B, and they are perpendicular to each other, which we call transverse. In other words, the waves are going that way, but the fields are pointing the other way. And as we said, we now have a whole spectrum of different electromagnetic radiations, different wavelengths, see what happened was Maxwell came out with this idea in 1860, and people said, well, how do we know you're right? So about 30 years later, somebody actually man-made radio waves by making a spark. He was able to create a spark, sort of like we do here with transformers, and he had another spark thing over here, and he was able to create enough electromagnetic radiation to spark the thing over here. And he said, aha, it's a man-made electromagnetic radiation going across empty space. That was about 1890, so about 30 years after Maxwell. It took him that long. It was very hard. They had very clumsy apparatus in those days. It wasn't as though you had all these things that we just buy in the store. Interestingly, 1890 roughly. By 1905 or so, 1901, Marconi, famous name, there's a little company in England called Marconi Electric. Marconi built a transmitter, sort of like what Hertz was the one in 1890, but bigger and stronger with a big antenna, and he was able to send a signal from Cornwall in England to Newfoundland, send a signal across the ocean, electromagnetic radiation, 1901. Marconi won a Nobel Prize for that in physics somewhat later. And you may know the story of the Titanic, 1912 or 13 around in there, this giant ship tried to cross the Atlantic. And because it was the best ship ever built, and with the most modern technology, it had radio on it. In fact, if you look at the pictures of the Titanic, you'll notice that it had this like tall pole from one end to the other. Check it out. That was in their antenna of this radio that they had built, the Marconi built radio. And the point was, when the ship hit the iceberg, they were able to send signals. And there was another ship, a new ship with this modern invention radio, the Carpathia, which was a few hundred miles away, but they heard the signals from the Titanic, so they knew to go there, because otherwise, how would you know? You got to give credit to the people who sailed across the ocean. Once you left land, there's no communication. You can send a carrier pigeon, what are you going to do? You're lost out at sea. But here, the Carpathia heard the signals and went to their rescue and saved 750 people about. 1,000 went down with the ship. But all of them would have been lost in that miserable, cold environment. They both had radio. In fact, if you're interested, you could look up the radio communications from the radio operator on the Titanic. They actually recorded his messages, and he stayed with the radio and he went down with the ship. Well, he signaled to the very end. Great. But anyhow, we now have all of these frequencies, different wavelengths, and they're produced by different means, depending on the wavelength size. For example, we're going to do a little demo here of a certain type. AM radio is around in here a megacycle, million cycles per second. FM radio is around 100 million cycles per second. Microwaves are up around a billion cycles a second. Cellular phones, your 3G, 4G, 4 gigacycles. We have light. That little spectrum right in here is what our eyes are able to detect, red to blue, the violet, as it were. Below the red is infrared, below red. Above is the ultraviolet above. We then get into X-rays and even shorter than that, gamma rays, which come out of nuclei. This is a broad picture. I did want to show you this, but this is actually what the use of the spectrum is, because the government assigns the frequencies, because otherwise everybody would be using whatever they wanted, and everybody would be on top of each other, and your radio would pick up, Joe is broadcasting from here, and Sam is broadcasting from there. It would be a mess. So the government organizes who gets the right to use certain parts of the spectrum, and it's broken up into all these things: police bands, naval bands, shortwave, ham radio, etc., etc. You can look in detail at this, but it's really amazing. And our TV channels, like Channel 2 is assigned certain frequencies, Channel 4 has certain frequencies, and it's the same all around the country. So that if you buy a TV set in California, you can use it in New York, because Channel 2 is a certain frequency range, and that's your set is tuned to those channels. When you click 2, it selects 2, 11, blah, blah. So, but then you're assigned that, because if everybody wanted to be on Channel 9, what would you get? A mess. So you have to know that. And that's what the big fight is about. Also, they talk about broadband and the rights to these things. This is public space. So the Federal Communications Commission, this is our space. And so they allot this. And they do a lot on the basis of what serves the public best, supposedly. Hopefully. In some places, it's not so honest. I understand that there was a minister of communications in India who was selling off the frequencies to his friends for a little consideration, shall we say. Well, they caught him, and he's sitting in jail now. And they reassigned all those frequencies that he gave away to other people for more honest purposes, or more, at least went through government scrutiny. Yeah, I have a note here that in February 2012, they voided 122 licenses that this man had given out because of it. So how do we generate, in particular, radio waves? Well, I can't go through it in great detail, but the point is, what you do, let me just start it out, and then you can finish. It's kind of fun to do this. You start out with a couple of wires attached to an electric generator. Well, I'll show you how a generator works. And then you can imagine something like this. Well, let me do it smaller. Let me do it here. I'm going to try to do it smaller so you maybe follow this better. You start out like this with a generator, and then you start with an electron. You put a plus charge here and a minus charge. We're going to do it very simply. So we know that you're going to get an electric field that goes from plus to minus, like that, right? Okay, but then you have this is a varying field. So at a later time, those charges will say move out a little further. You're getting a bigger dipole. In the meantime, this fellow, by the time this has moved this distance at the speed of light, let's say this is an electrical signal from here, moving at the speed of light. So here's where the speed counts. The signal from this generator can't get to here instantly. The fastest speed it can do is the speed of light. So this charge moves up at the speed of light. In the meantime, this pulse here, let me color it so maybe it'll look a little better. This pulse here moves out the same distance here. See, it moves out at the speed of light. Okay, and this one is created. Let me see if I can get another color. Not too many colors here. So let's say this fellow starts out here. Okay, and then in the next instant, this plus charge moves up to here, and the negative charge moves down to here, and it creates, let me make this one white. Okay, meantime, the blue one has moved out about the same distance to here, and this one has continued to move out like this. So as the charges move up, they also radiate outward. Then what you do is, this is the awkward part, I'm going to lose that. Let me maybe go over here. Let me begin again here. When he gets to the top, he creates another wave. In the meantime, these fellows have moved out further, and then this charge comes back down to 0. So what you get is a wave. Actually, it should be more like red, blue, white, moving outward at the speed of light as these electrons move up and down. So that's basically what's happening. You can see that this is going to produce the biggest field, because remember, the electric field is proportional to the dipole moment. This is a dipole, and with the charges far apart, the dipole moment is the charge times the distance. So this is going to produce a big field. So that would be, I really got it wrong here. This would be a weak field. This very first one is very weak because the moment is small, and then you have a bigger one over here, and yet a bigger one over here, and the biggest one is this one here, produced when the charge separation is the largest. So you build up this wave that's going out. Now, one of the features that you want to do, I have to show this, I've set up a couple of times already, and I don't want to do it again, so I'm going to do 2 demos at least, that this is to show that what you want is a resonating circuit, because the source, this sort of wiggly thing, has to be a resonating circuit, because you want a big amplitude of signal, because you're trying to propagate this wave, say, from San Francisco to Berkeley. So you need a resonance signal. What is resonance? Resonance is if you have a system that has a natural frequency. And the point is, if you can stimulate it with the same frequency from the outside, you get the amplitude to be very large. Now, the way we do that is that we have a wheel here that's going to turn, and I don't know if you folks over there, I don't know why you set up at an angle. The thing on the wheel is a little off-center. So as the wheel goes around, this off-center thing gives you an up and down motion about like that much. Right? It's this much off-center, so it's going to go around off-center like that. So this is sort of, yeah. So let's see. We turn it on, and you'll see that the motion at first is going around, and you see because it's off-center, you guys over there can't see much, can you? Is it okay? Can you see? Okay, so it's going around off-center, and it's lifting and dropping, and so the weight here, if it's free to move, is going to go down and up, about like that, about like that, right? So that's all it's doing. Okay, now, but I'm way off resonance, because this thing, you saw how it wants to go faster. So now I can turn this motor, and it will turn the thing faster. Now, it's still about more or less the same, right? Let me see if I can get the top and bottom. Yeah, it's pretty much, it's just the eccentric motion, off-center motion. Okay, now I'm getting closer to the resonance. Oh my God. Now you can see, sure as heck it's not going this way anymore. Let me see if I can get back on resonance. Now, it's not just because I'm going faster. It's actually because I'm just in step with it. I'm pumping it at the speed that it wants to go. Because if I even go faster, it actually makes things worse. See, now it's hard to move it on. So it makes things worse. So there was a peak in the response at the resonance. If you really want to see another dramatic, except this is medium dramatic, that's not good. But there's a Tacoma Narrows Bridge. Have you ever seen that? Look it up. Look at Tacoma, Washington built a bridge across a river. And it turned out that it resonated at about 30 cycles a second or something like that. And the wind, no, slower than that, but it could be simulated by slow wind. So it was blowing wind about 30 miles an hour one day, and it was just the right frequency to get the bridge going. And you can see pictures of the deck swaying like this, and finally crashed into the river. It was scary. You see a guy running away from his car. He's running like this. It's amazing. Here is a case in point. I don't have time to explain how we get a resonant circuit here. But there is a resonant circuit inside this apparatus. It's an inductance and a capacitance. And the energy is being resonantly shipped from inductance to capacitance, causing a frequency of about 85 megacycles, which is roughly the frequency of an FM radio. And it's transmitting from this antenna to this, and you can see that it's lighting up the thing. It radiates a dipole field. The lines of the field are this way, and so it's picked up by this antenna here. The electron's being driven back and forth, and so doing light the bulb. And what would you say if I turn, for example, if the electric field is going this way, if I turn it, I'm not going to show you, turn it this way, will you get current? You're saying no, and that's right, because now the lines are going this way, so you're just driving the current this way, you're not driving it through the bulb. Right? So there's your antenna. If you look on the roofs of some places, you'll see antennae this way. They're trying to pick up the signal being sent probably from the Sutro Tower. You know that big tower in San Francisco? No, so that's interesting. You don't get anything this way. You also don't get anything this way, because it doesn't radiate along its edge. It radiates this way. Right? Well, it should be very little at any rate. This may be getting in the way. Well, it's certainly weaker, if I could get it quite right. So you want to think about that. I guess we'll go into it in more detail later. Is it 4 o'clock? We will go into more detail later.